A. Intro. Hello students. Welcome to Sleepy Series. Tonight, we revise strength of materials. No pressure, no panic, just calm revision. Listen slowly. Let the concepts enter your memory naturally. Strength of materials is all about how bodies behave under load, how they stretch, how they compress, how they bend, how they twist, and how they finally fail. Remember one thing, every formula has a physical meaning. If meaning is remembered, formula becomes easy. Now relax and begin revision. Chapter 1. Stress and strain. Stress means internal resisting force per unit area. Formula: stress equals force divided by area. Sigma equals P by A. Unit of stress is Pascal. Normally in engineering we use megapascal. There are mainly three types of stress. First, tensile stress. It pulls the member, length increases. Second, compressive stress. It pushes the member, length decreases. Third, shear stress. Force acts parallel to area. Layers try to slide. Now strain. Strain means deformation per unit original dimension. It has no unit. Longitudinal strain equals change in length divided by original length. If body elongates, strain is tensile. If body shortens, strain is compressive. Hooke's law says, within elastic limit, stress is directly proportional to strain. Stress by strain equals constant. That constant is Young's modulus. Young's modulus is represented by E. Higher E means stiffer material. Steel has high Young's modulus. Rubber has low Young's modulus. Remember, stress causes strain. Stress is cause. Strain is effect. Now Poisson's ratio. When a body elongates in one direction, it contracts in perpendicular direction. Poisson's ratio equals lateral strain divided by longitudinal strain, represented by mu. For steel, Poisson ratio is approximately 0.3. Bulk modulus relates volumetric stress and volumetric strain. Shear modulus relates shear stress and shear strain. Important relation, E equals 2G into bracket 1 plus mu. Another important relation, E equals 3K into bracket 1 minus 2 mu. These relations are very important for objective exams. Let's recall E equals 2G into bracket 1 plus mu, and it's equal to 3K into bracket 1 minus 2 mu. Chapter 2. Bars of varying section. Extension of bar equals PL divided by AE, where P is load, L is length, A is area, E is Young's modulus. Extension increases with load and length. Extension decreases with area and modulus. Long bar stretches more. Thin bar stretches more. Flexible material stretches more. If bar has different sections, calculate extensions separately for each part, then add all extensions. Total deformation is algebraic sum. Temperature stress is also important. Thermal strain equals alpha into delta T. If expansion is prevented, thermal stress develops. Thermal stress equals E alpha delta T. Remember, free expansion means no stress. Restriction causes stress. Chapter 3. Principal stress and shear stress. At a point, stresses may act in different directions. Maximum normal stress is called principal stress. Maximum shear stress is called principal shear stress. For two-dimensional stress system, principal stress formula is sigma 1 and sigma 2 equals average of sigma x and y plus or minus square root of bracket. Sigma x minus sigma y by 2 whole square plus tau xy square. Maximum shear stress equals square root of bracket. Sigma x minus sigma y by 2 whole square plus tau xy square. Moore's circle is graphical method to find stresses. Center equals average normal stress. Radius equals maximum shear stress. Remember, planes of principal stress have zero shear stress. Planes of maximum shear stress have average normal stress. Chapter 4. shear force and bending moment. A beam carries transverse loads. Internal vertical force is shear force. Internal resisting moment is bending moment. Relationship: rate of change of shear force equals load intensity. Rate of change of bending moment equals shear force. At point load, SF diagram changes suddenly. At uniformly distributed load, SF diagram becomes inclined line. At uniformly varying load, SF diagram becomes curve. Maximum bending moment occurs where shear force becomes zero. Sagging moment is positive. Hogging moment is negative. For simply supported beam with central point load, maximum bending moment equals WL by 4. For simply supported beam with UDL, maximum bending moment equals WL square by 8. For cantilever with point load at free end, maximum bending moment equals WL. For cantilever with UDL, maximum bending moment equals WL square by 2. Remember these standard values carefully. They are frequently asked. Chapter 5. Bending stress. When beam bends, one side compresses, other side elongates. Neutral axis is line where stress becomes zero. Bending equation: M by I equals sigma by Y equals E by R. Where M is bending moment, I is moment of inertia, sigma is bending stress, Y is distance from neutral axis, E is Young's modulus, R is radius of curvature. Bending stress varies linearly. 0 at neutral axis, maximum at extreme fiber. Section modulus equals I by Y max. Bending stress equals M by Z. Higher section modulus means stronger section. I section is economical because more material stays away from neutral axis. Chapter 6. Shear stress in beams average. Shear stress formula: tau average equals V by A, but actual shear stress distribution is not uniform. General formula: tau equals VQ by IB, where V is shear force, Q is first moment of area, I is moment of inertia, B is width. For rectangular section, maximum shear stress equals 1.5 times average shear stress. For circular section, maximum shear stress equals 4 by 3 times average shear stress. Shear stress is maximum at neutral axis, 0 at outer fibers. I repeat, shear stress is maximum at neutral axis, 0 at outer fibers. Chapter 7. Slope and deflection. A beam bends under loading. Slope means angle of rotation. Deflection means vertical displacement. Double integration method, Macaulay method, moment area method, and conjugate beam method are used to find slope and deflection. Standard results are important. For simply supported beam with central point load, maximum deflection equals WL cube divided by 48 EI. For simply supported beam with UDL, maximum deflection equals 5 WL power 4 divided by 384 EI. For cantilever with point load at free end, maximum deflection equals WL cube divided by 3 EI. For cantilever with UDL, maximum deflection equals WL power 4 divided by 8 EI. Deflection increases rapidly with length, because length has cube or fourth power relation. Chapter 8. Torsion of shafts. Torsion means twisting. Power transmitting shafts work in torsion. Torsion equation: T by J equals tau by R equals G, theta by L, where T is torque, J is polar moment of inertia, tau is shear stress, R is radius, G is modulus of rigidity, theta is angle of twist, L is length. For solid circular shaft, J equals pi d power 4 by 32. For hollow circular shaft, J equals pi by 32 into bracket, d power 4 minus small, d power 4 bracket. Power transmitted by shaft equals 2 pi nt by 60, where n is rotation per minute. Hollow shaft is more economical than solid shaft, because material near center contributes less to torsional resistance. Chapter 9. Thin cylinders and spheres. Thin cylinder means thickness is quite small compared to diameter. There are two stresses, circumferential stress or hoop stress. Hoop stress equals PD by 2T. Longitudinal stress equals PD by 4T. Hoop stress is double longitudinal stress. Therefore, cylinder usually fails along longitudinal section. For thin spherical shell, stress equals PD by 4T. Sphere is stronger than cylinder. Chapter 10. Columns and struts. Column carries compressive load. Short column fails by crushing. Long column fails by buckling. Euler's formula. Critical load equals pi square E. I divided by effective length square. Effective length depends on end conditions. Both ends hinged. Effective length equals L. One end fixed, other free. Effective length equals 2L. Both ends fixed. Effective length equals L by 2. One end fixed, other hinged. Effective length equals L by root 2. Longer column means smaller buckling load. Radius of gyration, K equals root I by A. Slenderness ratio equals L, effective by K. Higher slenderness ratio means more chance of buckling. Chapter 11. Strain energy. Strain energy means energy stored due to deformation. For gradually applied load, strain energy equals P delta by 2. Proof resilience means maximum strain energy stored within elastic limit. Resilience is important in impact loading. Suddenly applied load causes double stress compared to gradually applied load. Impact loading produces very high stress. Rapid fire formula revision. Stress equals P by A. Strain equals delta L by L. Young modulus equals stress by strain. Extension equals PL by AE. Thermal stress equals E alpha delta T. Bending equation, M by I equals sigma by Y equals E by R. Shear stress formula, tau equals VQ by IB. Torsion equation, T by J equals tau by R equals G theta by L. Euler load equals pi square, EI by L effective square. Deflection of simply supported beam with central load, WL cube by 48 EI. Power transmitted, 2 pi NT by 60. Hoop stress, PD by 2T. Longitudinal stress, PD by 4T. Remember, stress is force effect. Strain is deformation effect. Remember, shear force changes bending moment. Load changes shear force. Remember, maximum bending stress occurs at extreme fiber. Maximum shear stress occurs at neutral axis. Remember, long columns buckle. Short columns crush. Remember, hollow shafts are economical. I sections are economical. Exam-oriented one-liners. Stress unit is Newton per millimeter square. Strain has no unit. Young's modulus is slope of stress-strain curve in elastic region. Neutral axis passes through centroid. Shear force 0 means possible maximum bending moment. Point of contraflexure is point where bending moment changes sign. For pure bending, shear force is 0. Maximum efficiency in transmission shafts is obtained using hollow shafts. Euler formula is valid only for long columns. Poisson ratio for incompressible material is 0.5. Ending, you have revised the core of strength of materials. Again and again, listen calmly. Revision through repetition creates long memory. Do not fear formulas. Every formula tells a physical story. Stress tries to resist. Strain tries to deform. Beams bend. Shafts twist. Columns buckle. And engineers learn to control all of them. Sleep peacefully and let your mind revise automatically. Good night, students.